Welcome to my lecture on improper integrals. We're going to be talking about the comparison theorem today. Okay, so I'm going to write down the comparison theorem. And the comparison theorem makes a lot of sense. Makes a lot of sense you draw a graph. Okay, so I'm gonna start off with that. But first, let's write down the premise. So in the comparison theorem, you have two functions, f of x and g of x, and they're continuous functions. And that should be b. And they're going to be continuous functions with f of x being bigger than or equal to g of x. And they're both greater than or equal to 0 for x bigger than or equal to a. Okay, so we want to think about the improper integrals here. Okay, so first I'm going to draw a graph, and I'm going to color code f and g. I think that'd be a good thing to do. So here will be g of x. I'll make it in blue. Sorry. Okay, so let's say g of x looks something like this. Okay, and let's say here's the value of a. So really what we're talking about is all this area. Okay, now we'll have another function f of x. I'll do that in black. Okay, here's going to be f of x. Here's its value at a. And the area here is all of that. Okay, all that the comparison theorem says about improper integrals is this. So conclusion, and there's two of them. One of them says that if this improper integral from a to infinity of f of x is finite, i.e. the improper integral converges, then logically, so does g of x. And you don't even need to compute the value of the limit of g of x, or the improper integral of g of x. And if I want to say why, it'd be because, or since, f of x being bigger than or equal to g of x, well, this implies that this integral from a to infinity of f of x dx is bigger than or equal to this integral from a to infinity of g of x dx. And since this integral converges, the one on the left, it has limit L, and that's less than infinity, then g of x also has to be less than infinity. That's the first conclusion that we can make from this comparison theorem. Okay. Our second one is this. If this integral of g of x is divergent, so it's equal to infinity, then so is the improper integral of f of x dx. And you might ask why, and it all comes from that inequality. So we know that f of x is bigger than or equal to g of x. And so the integral from a to infinity of f of x dx, after all, the black area is greater than the blue area, is bigger than or equal to the blue area. Okay. And the blue area is infinite. So f of x has to be bigger than infinity. So it must also be infinity. Okay, so it's divergent. Okay, and that's the statement of the comparison theorem. Let me do a brief example. Okay. Suppose I want to calculate this integral from 1 to infinity of x squared over x to the 8th plus x squared plus 1 dx. Okay. Well, this statement is true. X squared over x to the 8th plus x squared plus 1. Well, that's less than, because it has more stuff in the denominator, is less than x squared over x to the 8th plus 1. Okay, and that's less than x squared. I'm going to drop another term. Remember, x squared for x bigger than 1, between 1 and infinity. This x squared is going to be bigger than 1. And so if I drop it, I have less stuff in the denominator, making this bigger. And then I'm just going to drop the 1. So this is going to be x to the 8th, and this will be 1 over x to the 6th. Now, I don't actually want to compute this integral. I don't want to compute this integral because it's very difficult to integrate this integral. Maybe if you're lucky, some sort of substitution or partial fractions, but I just prefer not to deal with it. And I'll put less than or equal to here. It's less than or equal to this integral from 1 to infinity of this 1 over x to the 6 dx. Okay, and let's figure out if that is convergent. Okay, so this integral from 1 to infinity of 1 over x to the 6 dx, that's equal to this limit as b goes to infinity, this integral from 1 to b of 1 over x to the 6 dx. Well, we anti-differentiate this, and we're going to get minus 1 over 5x to the 5th. Okay, from 1 to b. Okay, then we just plug in these limits of integration. Okay, that limits to 0, and I'm going to add 1/5. So that's less than infinity, and we'd say it's convergent. Now, what this tells us is that we know that our final value here is 1/5. That's less than infinity, so they both converge. By the comparison theorem. Okay, and that was an example of the comparison theorem. That is all that we have for today. Thank you.